Hi and welcome. Today I'm going to continue talking about linear finite element theory, and this is part 4 in my series on this topic. The focus today is on how we can calculate stresses and how we can evaluate integrals of the principle of virtual work using Gauss points. So let's start talking about stresses. Last time I showed how we can calculate the strains from nodal displacements. And if we know strains, we can always calculate stresses, in this case using Hooke's law. Since we're focusing on linear finite elements, we can use a linear elastic representation. And now here's one equation for that. It's written in terms of mu and lambda. And for plane strain, which is the focus of our series here, and the stresses can be calculated from the strain components, as shown here, directly from this equation. But we like to express this in terms of a Young's modulus and a Poisson's ratio instead of the mu and lambda parameters. So we have to substitute these based on the values that's shown in this table to the right. And if we go through that exercise, we can show then that the stress matrix is given by a stiffness matrix C times the strain matrix here. And this stiffness matrix have to have this form by simply plugging it into this Hooke's law and doing the substitutions. So now we have an expression that shows us how we can calculate the stress components from nodal displacements. And that's really cool. We'll use that in a little bit. Next, let's go back to the principle of virtual work. So here's the internal virtual work on the left. It has this summation over all elements, but then for each element, we need to calculate this quantity, this integral. And how do we do this? This is a little bit tricky, but the way we do it is to do it in 2 steps. The first step, no surprise, is to introduce shape functions. So the element that we want to integrate over is pretty complicated in shape. So we switch variables using shape functions to get it into this coordinate system here. And an integral over the volume, or in this case an area, since it's a 2D problem, will be given by the equation down here. So area integral over f becomes area integral over f of the new variables, psi and eta, but we also need to multiply by the area factor. So that's how much the area has changed when we did the substitute variables. And that's given from the shape functions that's shown down here. So that's the first step, change of variables. The second step is to, instead of calculating an integral, we're going to calculate it in numerical way using Gauss quadrature. So here's the 1D example from Wikipedia that shows that the integral from -1 to 1 of a function is basically a weight factor, constant, times the function evaluated at 1 or more points. So this is how Gaussian quadrature works. In our case, we have an area integral. So here we go. We have the integral here that we want to evaluate. We substitute the integral with a double summation. Of course, we now have 4 integration points, or Gauss points, at which we need to evaluate this function in order to calculate the value of the integral. And the Gauss points, the points we want to use to evaluate the functions, are listed here. These are selected. These are the ones that are selected in this method to get the best accurate results in general. So there are 1 over square root 3 plus and minus. The weight factors in this case end up being 1. So they're all 1. So there's the equation for that. We just need to evaluate this, and it's very easy to do, right? So therefore, we can calculate these area integrals in very quickly and numerically accurately way. So if we go back to the first term of the principle of virtual work here, the internal virtual work, we're going to see if we can calculate this now, express this in a different way that is better to work with. So the first thing we do is recall, well, the virtual strain is basically B times the virtual nodal displacement. So that's known. In our equation here, we have the transpose of that. So we have to take the transpose of this matrix equation. When you take the transpose of the right-hand side, you have to switch the order, or reverse the order, as you can see here. The stresses, similarly, are given by the equation that I just showed earlier in the video. We can put this all together, and this is what we end up with. When you take the transpose here, we get the virtual nodal displacement. But that's not part of the integral. It's a constant. So we can move that outside this integral itself. And similarly, the nodal displacement can be moved to the right. So we have this quantity before and this one behind, and this is the nodal, the element stiffness matrix, given by this tensorial quantity, which we're now going to convert to a numerical calculation using Gauss points and Gaussian quadrature. And that becomes this equation here. So we sum over all the Gauss points, and B is a matrix that depends on where the location of the Gauss point is and the nodal locations. So we can calculate all of these quantities, and we can assemble this matrix for each element in our problem that we want to solve. And then we still don't know what to do with these quantities. Then I will come back to that next time. It turns out that you can actually solve for the nodal displacements once you have done all of this and repeated this for their other terms in the virtual work equation. So it's a little bit abstract at this point. You will see, though, that we can assemble all of this together and get a big global matrix of all the displacement as a function of stiffness, and we can calculate what that is. But that's something I will show next time. If you have any questions, you can ask them below.